In this final section in integration, we're going to look at some more applications of integration to build on the ones we looked at last session on linear motion and kinematics. So in that context, we were looking at displacement, and we said how the rate of change of displacement with respect to time gave us the velocity. So if we were trying to find, if we had the rate of change or the velocity function, we could integrate that, and that would enable us to find the distance or the displacement depending on what we're after. And what we're going to have a look at now is some other examples of how we can integrate a function to give us some information that we are interested in. And we're assuming that our starting point is a function which itself is a rate of change. And we're going to have a look at an example here in the context of bacteria, which you can see in the background. So we know that essentially here the integral of a rate of change is the total change from T1 to T2. So what does that mean? Well, let's have a look at this example with bacteria. So suppose we have a culture of bacteria which starts with an initial population of 100 bacteria. The rate at which the number of bacteria changes over a 1 month period can be modeled by this function here. So RT, so R is the rate of change of bacteria. So this is the change in the population with respect to time. So that's R, the rate. And we know that is equal to e to the power 0.273 t, and that's where R is measured in bacteria per day. So this is the change in the population with respect to time per day. So in this instance, our function is the rate of change of population. So if we integrate the rate of change of population, we should end up, or we should be able to find out the total change in population over the period. We are asked in the question to find the population of bacteria 20 days after the culture was started. So let's have a look at how we can try and dissect this question. So we know that this is a rate of change, so it is in itself the derivative of a function. It's the derivative of the population function, because if we have the population function and we differentiate it with respect to time, we end up with the rate of change in population, which is what we've got here. So therefore, if we integrate this function, we should end up with the capital R. Remember the antiderivative used, we use capitals to distinguish that. That will give us the number of bacteria at time t, or more obviously the population. So we've got our rate of change here. If we integrate that between 0 and 20, we know that's going to be the same as the the population at 20 after 20 days minus the population at 0 times 0. So we have got our function here, which is e to the power 0.273t, and we integrate that with respect to t, and that gives us 857 bacteria. This, however, is not the final answer, because this constitutes the change in population between time t equals 20 and time t equals 0. So we know that we've got a change of 857 bacteria over the period. However, we also know that the initial population was 100 bacteria. So the population after 20 days, which we're asked to find, is going to be this difference in the population. So the population here at 20 minus the population at the time equals 0. Therefore, that's going to be 857 plus 100, which is going to give us 957 bacteria. Now, that's the more straightforward way to do it. It's a bit more intuitive. There is an alternative way of doing it, and that is using this law here. So if we've got an exponential here, we integrate it, we should be able to from early work, remember that's the same as 1 over a e to the a plus b plus c. In this instance, then, we could find the indefinite integral for this by saying it's 1 over 0.273 e to the 0.273t integrated with respect to time. That becomes this, 1000 over 273. And we know that the initial condition R0 is 100. So if we substitute in for 100 when time equals 0, we can solve for C, which will give us 100 minus 1000 over 273, which we can simplify to that. And then that would give us an expression here for the population at time t, which you can see is a little bit unwieldy. If we then substitute it for 20, that will also give us the right answer, but it's a little bit more long-winded. Either of those options work, but that is an example of how integration can be used, the integration of a rate of change function. If you integrate a rate of change function, you can ascertain the initial condition. So here we're looking at a rate of change of population with respect to time. So if we integrate it with respect to time, we can get back to that initial population.